Lesson number 2. What is a neural network? Hello. In the previous lesson, we understood the difference between machine learning and deep learning. We saw that deep learning allows the model to learn the representations by itself without us having to choose features for it. Now, we're really going to dive into the internal structure of neural networks. Let's start with the most basic unit, the artificial neuron. A neuron receives input, usually a vector of numerical values, performs a weighted sum on them, adds a bias, and then applies a nonlinear function to the result called an activation function. The formula looks like this, where x is the input vector, for example, pixel values in an image. W is the weight vector. These are numbers that multiply the inputs and affect their relative contribution to the resulting output. B is the bias, an additional number that is added to the sum and allows the neuron to change its output even when all the inputs are 0. Phi is the activation function. We'll get to it in a moment. The neuron is a simple computational unit, but when you connect hundreds or thousands of such neurons into layers, the result is a system that can learn especially complex patterns. The activation function, meaning the S. It's a critical component. If it's not nonlinear, for example, if phi of x equals 3 times x, the entire network will remain linear and won't be able to solve complex problems where the relationships between pieces of information are nonlinear, which is very common in the real world. That's why activation functions are nonlinear. Two of the most common ones are ReLU, rectified linear unit, where phi of x equals the maximum between 0 and x. If x is negative, the output will be 0. If it's positive, it passes through as is. This formula is simple, fast, and very common in deep learning. The second function is sigmoid. Phi of x equals 1 divided by 1 plus e to the power of minus x. This function produces an output between 0 and 1. It used to be used a lot in the past, but today it's a bit less common, mainly because of the vanishing gradients phenomenon that occurs when training especially deep networks. It refers to the phenomenon where the gradient values become very small, and then after applying the activation, they might become 0, actually disappear, which leads to the training diverging.
If you notice that the error isn't decreasing, check if you accidentally chose sigmoid instead of ReLU.
Now that we understand what a neuron looks like, let's talk about the different layers that characterize deep neural network architectures. Each layer has a number of neurons, each of which receives the output from the previous layer and passes its output to the next layer. The first layer is called the input layer. It receives the actual data, x. The last layer, the output layer, provides the final prediction, y. And in between, there are the hidden layers. This is where internal processing takes place, and the network learns hidden patterns. Every connection between a neuron and the next layer has a weight, and each neuron also includes a bias. These are the values the network will learn during the training process. The process that describes the flow of information from input to output is called the forward pass, because the information moves from layer to layer until it reaches the output layer. Here, the question arises, are all the layers identical? Structurally, yes, they are all made up of neurons that compute y equals f of wx plus b. But in terms of their role, no. The output layer usually uses an activation function that matches the type of problem. For example, sigmoid for binary classification or softmax for multiclass classification. The hidden layers usually use ReLU. Let's now focus on basic networks of the MLP type, multilayer perceptron. These are networks where every neuron is connected to all the neurons in the next layer, which is why the layer is called fully connected. Our first example will be a classification problem. A problem where the prediction is discrete. Let's look at the XOR function. A simple function, but not linear. What I mean is that there's no straight line that can separate its two groups of data.
I once tried to solve XOR with linear regression. It just doesn't work. Then I built a network with one hidden layer, and it solved it perfectly.
Thank you, Mita. That's a good example. The XOR function is not linear, it has a non-trivial dependency between the inputs. Let's describe it. Two inputs, values of 0 or 1. It outputs a value of 1 only if the inputs are different. The nonlinearity in XOR comes from the fact that there is no straight line that can separate the four input pairs so that the outputs of 1 and 0 are completely separated, as shown here in the graph. Therefore, a network with an input layer of size 2, a hidden layer with 4 real neurons, and an output layer with 1 neuron can represent the function because it includes a nonlinear element. And at the end, we also added a sigmoid. If we don't use activation, meaning if all the neurons are just linear layers, then the combination of several layers still creates a linear function, and therefore we won't be able to solve the XOR problem. That's why it's very important to include activation functions in the architecture. To sum up, a neural network is a sequence of layers of neurons. Each neuron calculates the weighted sum of its inputs with the weights, adds a bias, and then applies an activation function to allow for a nonlinear model. The output of one layer is the input to the next layer. The weights and biases are learned during the training process. Even nonlinear problems can be solved with a simple network like an MLP. In the next lesson, we'll see how the training itself is done. What is the loss function and how do the weights change during training?